Hey guys, welcome back to another set of chemistry notes for Unit 3 about the electron. In the last video, we talked about how electrons fill up orbitals and we saw one example. In this video, we are going to talk about the different ways that we can show that happening. The first notation we're going to look at is called orbital notation. And in orbital notation, each individual orbital is represented by a line or a box. Each individual electron is represented by an arrow. And this notation is also known as an orbital diagram or as orbital electron configuration. So let's take a look at this. Our first example we're going to talk about is hydrogen. So you should look on your periodic table, find the square for hydrogen. When you find it, you'll see there's a 1 above the symbol for hydrogen, meaning it has atomic number 1. For right now, atomic number always means number of protons, and for right now, it also means number of electrons. So since hydrogen is atomic number 1, that means it has 1 total electron. We are going to go ahead and draw in those electrons to our orbitals. So remember, the very first orbital, your lowest energy orbital, is the 1s orbital. Right? Start with your lowest energy level, so the smallest number, which is 1, and your lowest energy orbital, which is your s orbital. So we'll draw our 1s orbital, and we'll put a single electron into it. So that's your orbital notation for hydrogen. The next question is how many valence electrons are in hydrogen? And there are two ways you can figure this out. One is to look at the group number, the family number, the column number for hydrogen. So look at hydrogen on the periodic table, find the box that it's in, and then look above the box, and that is family number 1, group number 1, which means it has a single valence electron. You can also tell from the orbital diagram how many valence electrons are in an atom. You find the highest energy level, so in this case there's only one energy level, it's the first energy level. Any electron in that energy level is a valence electron. So this electron here is a valence electron. There's one of them. So hydrogen is our easiest example because it only has one electron, but it doesn't always make everything super clear. So let's look at another one. Our next example is boron. So you need to go find the periodic table, find boron, and when you find the box that has boron in it directly above it, you will have a 5. That means that boron is atomic number 5, which means that it has 5 protons and 5 electrons. We're going to arrange those electrons into orbitals. So we will draw our very first orbital, 1s, and we will put electrons in it. So we'll fill with our first electron, and then our second electron, before it's going to move to a new orbital, to a new higher energy, it's going to fill in right here. Remember, electrons are lazy. They don't want to move to a higher energy unless they absolutely have to. So since there was room in this orbital, our second electron will fill in here. But that's only 2. We need 5. So we'll draw another orbital. After 1s comes 2s, and then we will put electrons into this orbital. So I'll fill in my third electron, and then my fourth electron, but again, I need 5 electrons, so I will move on. After 2s comes 2p, and remember your p orbitals come in sets of 3. P is 3. So I'll draw my 1, 2, 3, 2p orbitals. This is called the 2p subshell. Remember, if it has a number and a letter, it's a subshell. So I'll draw my 2p subshell, and I have 4 electrons. I need 5, so I'll just put 1 more electron. And that's my orbital notation, my orbital electron configuration for boron. And now I need to figure out how many valence electrons there are. So I can either look on my table, find the box that has boron, and then look above it for the family number, which is 3, and that will tell me that there are 3 valence electrons. Or I can look on my orbital notation, My highest energy level in this orbital notation is the second energy level. Of all of the numbers you see here, 2 is the highest number. So any electron in a 2 kind of orbital is a valence electron. So this is in a 2s, that's a 2, so that's a valence. This is in a 2s, that's a 2, so it's a valence. And this is in a 2p, which is a 2, so this is valence. So that is 1, 2, 3 electrons. So I have 3 valence electrons. Those will always agree with each other. Let's look at our next one. Our next example is magnesium. Finding magnesium on your periodic table, it has 12 electrons. If you look in the box for magnesium, it's got a little 12 above it, means it's atomic number 12, 12 protons, 12 electrons, for now. Then we can draw our orbitals. And I'm just going to draw them all straight out this time. I'm going to tell you that we need to go our first orbital, 1s, always. Our second orbital is 2s, always. Our third subshell. Quick note, this is the 1s orbital. It's also the 1s subshell. A subshell can be just one orbital or it can be a whole group. So this is our 1s subshell, our 2s subshell, then 1, 2, 3, our 2p subshell, and then our 3s subshell. And I'll tell y'all that that's where we're going to stop. We don't have to go any farther than that. And then we can go fill in our electrons. And I'll put in 1. And again, before I go to my higher energy 2s subshell, I'm going to completely fill in 1s. So that's 2 electrons. And then number 3. Then before I move on to 2p, I will completely fill in my 2s subshell, remembering that if 2 electrons are sharing an orbital, they have to have opposite spins. Because remember, we learned that electrons are lazy, electrons are selfish, electrons are followers, but they are not identity thieves. So that means that we'll have electrons filling in our lower energies before they move on. They won't share unless they have to, but they are not going to have the exact same properties if they're sharing a room. Since they're sharing an orbital here, sharing a room here, they're going to have opposite spins. One points up, the other points down. Okay, that was 4 electrons. We'll move on to our 5th. 1s and 2s are full, so now we can start filling 2p. I'll put an electron right there. Then our 6th electron comes along, and it's going to fill this orbital because all 3 of my 2p orbitals have the exact same energy. They are identical orbitals, they're just arranged differently on my different axes. One is on the x-axis, one is on the y-axis, and one is on the z-axis. So these are all equal energy, they're like identical rooms, and electrons are selfish. So they're not going to share if they have another room available to them that doesn't make them use up more energy. So there goes my 6th electron, and then my 7th will fill in over here because once again, they're selfish, they don't want to share. And since they are not sharing, they are followers, right? They all have the same spin. Since they're in different orbitals, they all have the same spin. But now electron number 8, rather than move on to 3s, which is a higher energy, we're going to double back and make them share now. So I'll put number 8 right here, and since now they're sharing, they have to have an opposite spin. Number 9, now that they are sharing, they have an opposite spin. Number 10, now that they're sharing, they have an opposite spin. And now that my 2p subshell is full, I can move on to 3s. And I will draw my first electron pointed up. That's number 11. And I will draw my second electron pointed down, number 12. So that is my orbital notation for magnesium. Once again, I need to label my valence electrons. My highest energy level here is the 3rd energy level. So any electron in the 3rd energy level is a valence electron. So this is a valence electron, and this is a valence electron. So that is 2 valence electrons. And if you look on your periodic table and find the square for magnesium, if you go all the way to the top of that column, you will find a 2 at the top. So that also tells you that there are 2 valence electrons in magnesium. All right, example number 4 is arsenic. If you find arsenic on your table, it is number 33, meaning it has 33 protons and it has 33 electrons. So we're going to go ahead and draw our orbitals, and this time we're going to go all the way through the 4p orbitals. So make sure you write kind of small for this one. So I'll draw my 1s and my 2s and my 2p and my 3s and my 3p. Now take a second, look at your table. We've got your periodic table here. Isn't it beautiful? Remember that if this is my 4th row, these are my 3d orbitals right here. So I've read across, this is 4s and then 3d. Just like up here was 3s and 3p. Remember, you read your periodic table like a book. So we've read across 3s and then 3p. Start a new line, 4s. So I'll draw my 4s orbital. Then after 4s comes 3d. And your d orbitals come 5 in a set. Look at your very first page of notes from this unit. D orbitals always come in 5s. So I'm going to draw 1, 2, 3, 4, 5 3d orbitals. And then I'll keep going. 4p comes next. These are my 4p orbitals. And your p orbitals always come in sets of 3. So I will draw my 1, 2, 3, 4p orbitals. And that's the farthest I need to go. Now I'm going to fill in my electrons. Even if you know you're going to fill up all the way to the right, still get in the habit of filling in your electrons correctly. Don't just go down the line all in a row. So I'll do number 1, number 2, 3, 4, 5, 6, 7. Yes, I'm going to fill up all of my 2p orbitals, but it's still a good habit to do 1 in each orbital and then go back and double up. Build good habits. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, almost there. I have 3 left, so this is where it really matters that you follow your rules. I'll put number 31 right here. Electrons are selfish, so number 32 won't share since it doesn't have to. It'll go here, and then number 33 will go right here. So this is your orbital notation for arsenic. And if you look on your periodic table, you will see that arsenic is in the 5th family. But we can also see that in our orbital diagram, our highest energy level, and this is where it gets a little weird, our highest energy level is the 4th energy level. So I have my 4s and my 4p that are both in the 4th energy level. The only valence electrons are the ones that show up in these 2 subshells. So this is a valence, this is valence, 3, 4, and 5. So those are my 5 valence electrons. 3d orbitals are not ever going to be valence electrons, only s and p orbitals. So here I have my 5 valence electrons. And here I'm going to make your life a little bit easier. The 5th example in your notes says PM, promethium. We are not going to do promethium. We're going to do cadmium instead. So when you look on your periodic table, you will see that cadmium is number 48, which means that it has 48 electrons. So we're going to draw 48 arrows. Before we do that, let's look at where cadmium is on the periodic table, see if we can figure out how many subshells we have to draw. So let's backtrack a little bit. We started with hydrogen, which is right here on your periodic table. All right, so I filled in my beautiful periodic table a little bit farther. Hydrogen is number 1, and it is right here. Remember, this is the S block of your periodic table. So hydrogen, the element is in the first row of your table in the s block, and its orbital notation ended in the 1s orbitals. Boron is right here. Boron is in the second row of your table in the p block of your table, and its orbital notation ended in the 2p orbitals. Even farther, boron is the first element into the 2p orbitals, and there was 1 electron in our 2p orbitals. Magnesium is number 12. Magnesium is right here. It's in the third row in the s orbitals, but it's not the first element, it's the second one. And if you look in your orbital notation, the orbital notation for magnesium ends in the 3s subshell with 2 electrons. So third row, s block, 3s orbital, 1, 2 elements there, 1, 2 electrons. Let's look at arsenic. See if you can pick up on this here. Arsenic is right here on your periodic table. It's in the fourth row in the p block, and it's the 1, 2, 3rd element. If you count across from where the p block starts right here, you can count 1, 2, and then the third one is arsenic. And if you look at the orbital notation, arsenic ends up in the 4p orbitals with 1, 2, 3 electrons. So now let's look at where cadmium is on our table. It is right here on your periodic table. It is in the 4d orbitals, and it is the 10th element. If you count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, cadmium is number 10. So if the trend continues, the last subshell we should draw is the 4d subshell, and there should be 10 electrons in it. Let's see if that's true. So I'm going to draw my orbitals, my subshells in order, and again, you're going to want to write small for this. Draw my 1s, and then my 2s, and then my 2p, and then my 3s, and then my 3p, and then my 4s, and then my 3d. Remember 4s and then 3d. 1, 2, 3, 4, 5 of them. And then back up to 4p. Same order every time. And then after 4p, we come back, start a new row. That is 5s. I'll continue it down here. And then after 5s comes 4d. So 1, 2, 3, 4, 5 of my 4d orbitals. And now I'm going to fill those in with 48 arrows, 48 electrons. 1, 2, 3, 4, 5, 6, 7, build good habits, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, almost there, 37, 38. And now that I'm in my last subshell, this is where I definitely need to be careful to follow the rules. 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. There's my 48th electron. Look at your last subshell. It's the 4d subshell. There are 10 electrons in it, just like we said there should be, according to our periodic table. So you can kind of predict what your orbital notation is going to look like before you've actually drawn it. And you can use your orbital notation to predict what element you're looking at. And we'll see that in just a second. Right now, let's identify our valence electrons. Our highest energy level is not this last orbital. It's not 4. It's actually 5. We hit the 5th energy level and then came back down to 4d. So our valence electrons are the ones in any kind of 5 orbital. So this electron here in the 5s, this electron here in the 5s, there are 2 of them, so there are 2 valence electrons. You can't always just look at your last subshell. You need to look at all of your subshells, find your highest number, and go from there. So a second ago I mentioned we can use orbital notation to identify elements. We're going to look at that now. All right, so here we have an orbital notation pre-drawn. We're going to use it to identify what element this is. And there are 2 ways you can go about this. Depending on the element, probably the easiest thing to do is just count up the electrons. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've got 15 electrons. We should go look at our periodic table and find the element that has atomic number 15. And if you look at your table, you will see that that is nitrogen, right? It's got a 15 above it. You have your 14.01 underneath it, but this is the magic number, 15 electrons, atomic number 15. This is nitrogen. The other way you can tell is by looking at where those electrons are. This element, whatever it is we're looking at, will be in the 3p orbitals in the 3p subshell, and it'll be the 3rd element in. So if you go to your periodic table, find the 3rd row, find the p block, and count 1, 2, 3 from the left, your finger will be sitting on the square that says nitrogen. So either way will work for now. Soon we're going to see that sometimes electrons don't actually behave like this, and then it'll be safest to just count your electrons. But for right now, either method will work. So now is a good time to practice. Turn the page. I know that there's still some blank stuff on the page you're looking at. That's okay. For now, turn the page, find page 18. There is some practice at the bottom of page 18. You don't know how to fill in that entire box yet, but you can fill in where it says total electrons and valence electrons, and you can fill in the blank to the right that says ON for orbital notation. So go ahead and fill in the total electrons, the valence electrons, and the orbital notation for calcium on page 18. And if you turn to page 19, there are many more practice problems for you. At the bottom of page 19, the last 2 problems, we're going to change to bromine and xenon. So the second to last problem is bromine. The last problem is xenon. If you are having trouble picturing what I mean, you can pop over to my website. The key is already posted, so try to avoid the answers and just look at the left-hand column where I've replaced some of the elements to make your life just a little bit easier. You're welcome. And while you're doing this, practice highlighting your valence electrons because they're highlighted in the key. So practice highlighting them, picking them out, seeing where they are in the orbital notation, and making sure that they match the number that you predict you should have. So take a minute, do that practice, check the key on the website, and when you're ready to look at the next configuration, which will be less writing, go ahead and unpause the video and we'll start again. All right, our next notation we're going to look at is called standard electron configuration. And it conveys all the same information. It talks about each subshell and it tells you how many electrons are there, but it eliminates the lines and the arrows. You don't have to draw each individual electron. You're still going to talk about each individual subshell, but you're going to group all of the electrons within that subshell together, and you're going to get something that looks like this. It'll be your number, still, that tells you the energy level, and it'll be the letter that tells you specifically which subshell are we looking at. But then instead of drawing a line and like filling it with arrows, you're just going to write a number. And it says, within my 1s subshell, I have 2 electrons. That number is your number of electrons. You can just write them all with one number instead of drawing them individually. And this is also known as complete electron configuration. It's called this because we're still talking about every electron. Our next abbreviation is going to cut a whole bunch of that out. So for right now, we're still talking about every electron. It is the complete electron configuration. So we're going to look at some examples. They might look familiar. We just did them. So you can sort of compare what we're about to do to what you have written down in your notes already. All right, let's look at hydrogen here. Hydrogen, remember, has a total of 1 electron. We can go ahead and draw our beautiful periodic table here, or you can just flip back and forth. I'm going to draw my beautiful table. I'm nothing if not an artist. Hydrogen, remember, falls right here on your table. First row, S block. So and this should say standard electron configuration, is only going to have to talk about the 1s subshell. These are all your s's over here. So we'll write our 1s subshell. Within there, there's only one electron. So we'll write 1s, 1. And that's it. It's not really a whole lot different for your very short elements, but when we get into those longer ones, you will appreciate it. So our standard electron configuration for hydrogen is 1s1. We said there should be one valence electron, and we can see that right here. This one electron is our one valence because it's in the highest energy level. Let's look at boron. Remember, boron is over here. It's right here in our 2p subshell. So once again, we will talk about every subshell up to and including 2p. So 1s is full. It has 2 electrons, right? We're just reading across our table. 1, 2, full. And then we finish that row, start here, 2s. 1, 2, full. Then comes 2p. And boron is the first thing there. So it's 2p with only 1 electron. So 2p1. You also know you're done when your superscripts add up to your total number of electrons. Boron has 5 electrons, and 2 plus 1 is 5. So we have 5 electrons here, 5 electrons here. We are all set. Let's go ahead and highlight those valence electrons. According to our table, there should be 3 of them. Our highest energy level here is 2, right? 2s, 2p. So these 2 electrons are valence, and this electron is valence. 2 plus 1 is our 3 valence electrons. So far, so good. Let's look at our next one. Magnesium falls here on your periodic table, right? It's in the 3s subshell. It's the second element, the second electron in there. So we are going to have to fill up 1s completely. We'll fill up 2s completely, 2p completely, and then 3s, there will be 2 electrons. So let's go ahead and fill up our orbitals. We'll start with 1s. We said it should be full with 2 electrons. And then 2s should be full with 2 electrons. And then 2p should be full with 6 electrons. And then next comes 3s. We said there should be 1, 2 electrons there. And if you look on your orbital notation for magnesium, it says the exact same thing. It's just all drawn out. It's got a line with 2 arrows for 1s. It's got a line with 2 arrows for 2s. It has 3 lines with 6 arrows for 2p. And then it's got a line with 2 arrows for 3s. All the same information, just a little bit less writing involved. And to double check ourselves here, 2 plus 2 plus 6 plus 2 is 12, which is the number of electrons we said we should have in magnesium. We also said magnesium should have 2 valence electrons. So we'll find our highest energy level, which is the 3rd energy level, and within it there are 2 electrons. So there are 2 valence electrons. Moving on, let's look at arsenic. Arsenic, we said, should have 33 electrons. When we find arsenic on our table, it is right here, and it should be the 1, 2, 3rd element. So we should end up in the 4p subshell with 1, 2, 3 electrons. That's where we should end up. So let's go ahead and try that. So we'll do our 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and remember after 4s comes 3d, so 3d can hold 10 electrons, and then after 3d we go back up to 4p. Said there should be 3 of them. Let's check to make sure that works out. 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 3 gives you 33. So that is the correct answer. This is our standard electron configuration. Still a bit of writing, but definitely faster than drawing all of our lines, all of our arrows. Let's go ahead and check our valence electrons. We said earlier that arsenic should have 5. So if you look on the table, it's in the 5th family, 5th group, 5th column. Should have 5 valence electrons. Our highest energy level here is 4. So we have 4s, 4p. These electrons here are valence, and these electrons here are valence. And 2 plus 3 is 5 valence electrons. All right, last one. Let's look at cadmium. So cadmium is in your 4d orbitals. It's the 10th thing in there, remember? So it's right there on your table. So we should end with 4d, because these are the 4d orbitals. So the last thing we write should be 4d 10, because this is the counting across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th element there. Again, you can't really see that in my picture. Look at your periodic table, prove it to yourself. And here we go. We're going to fill in all 48 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, don't forget that, 4p6, 5s2, 4d10, and that's it, right? And if we add these all up, 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36, plus 2 is 38, plus 10 is 48. 48 electrons, and it all fit in the box because we didn't have to draw each one individually. Let's go ahead and highlight our valence electrons. Our highest energy level here is 5, so these 2 electrons right here are the valence electrons. There are 2 of them. All the same information that we had from our orbital notation, and it's just a little more condensed. It's the only difference. And just like with your orbital notation, we can use this to identify elements. Once again, probably the easiest way to do this is just add up all of your electrons. So 2 plus 2 plus 6 plus 1, that is 11. Go to your periodic table, find atomic number 11, and you will see that it is sodium. Coincidentally, sodium is also in the 3rd row in the S block, and it is the first element there. So that tells you that this element here is in the ground state. Everything is in the ground state for now, but this will be a useful skill starting 3 videos from now. Looking at our next one, we have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17 electrons. Looking at your periodic table, 17 electrons are chlorine. Atomic number 17 is chlorine. And once again, chlorine happens to be in the 3rd row in the P block, and if you count across, it's the 5th element there. So this is chlorine in the ground state, as it should be, because we haven't learned anything else yet. All right, now is your chance to practice your standard electron configuration. Go back to pages 18 and 19. Now that box that says SE, you can fill in with your standard electron configuration. Try and do it without looking at the orbital notation, but then go back and make sure that they match. And then go check on my website, look at the key, make sure you've done it correctly. Because the next thing we're going to do is going to look a whole lot like standard electron, but it's going to be even shorter. So when you're ready to move on, unpause the video and we'll talk about our last type of notation. All right, our last notation is called noble gas configuration, and it's an even shorter version of what we were already doing. It's a shorthand of standard electron configuration. It's called noble gas configuration because it utilizes a noble gas. Noble gases all have their valence level completely filled. For all of them except for helium, that means they have 8 valence electrons. 2 electrons in the s orbitals and 6 electrons in the p orbitals because those are always the highest energy. For helium, it does not have a p orbital. It only has an s orbital. So for helium, a full valence means 2 electrons. But in any case, it is a full valence level. So you're going to pick a noble gas and base your electron configuration around that. And the way you pick your noble gas is to find the one in the energy level, and I should say it's going to be in the row above the element of interest. So above, but instead of saying energy level, because that can be a little confusing, we're going to say row. So you will look at your table, you will find the element you are looking for, go up 1 row, find the noble gas in that row, use that. Here's what I mean by that. So I'm going to draw my beautiful periodic table once more. Okay, so here's your wonderfully drawn periodic table, including the noble gases that are listed on your periodic table off to the right. Helium, neon, argon, krypton, xenon, and radon. The table in your booklet, the table you'll have on the test, doesn't include the 7th row noble gas, which up until very, very recently has just been called Ununoctium because it's number 118. The proposed new name, because its existence has been proven, its proposed new name is Oganesson with the symbol OG, which is a little ironic considering it's the newest noble gas, but that is the element that goes underneath radon on your periodic table. And you don't need to know that. It's just some fun periodic table trivia for you. So we've scrambled up our examples a little bit here. There's really no way to write hydrogen in noble gas configuration because there is no noble gas above hydrogen. So we've shifted everything up and added a new example of argon to the bottom. We're going to go ahead and write out our, once again, this should not say orbital notation. This is your noble gas configuration. We're going to follow the same steps we were following before. Boron has 5 total electrons. Here's boron. Boron is on your table right here in the 2nd row. So to find the noble gas above boron, find it on the table, go up 1 row, and then go to the end. And the noble gas above boron is helium. So we're going to use helium. We're going to take helium and write it down. We're going to put it in some square brackets to show this is what we are doing. And then anything in helium's electron configuration, we don't have to write again. It's covered. We can just start from where helium left off. So that means we have finished this 1st row of the table. We're free to start on our 2nd row and just write 2s2 2p1. So this has all the same information that the original did, the standard electron configuration did. We're just using helium to take part of it out. So initially we had 1s2, 2s2, 2p1 as our configuration for boron. So we've just taken out this 1s2 and replaced it with this helium. That's all we did. And you can still see in your noble gas configuration 2 and 2, these are our highest energy levels. So this is valence, this is valence. We have a total of 3 valence electrons. Nothing has changed, just a little less writing. All right, let's look at magnesium. Magnesium is number 12 on your periodic table. Magnesium is right here. So to find the noble gas we need to use, we will go up 1 row to the 2nd row and find the noble gas there. That is neon. So we'll start by writing neon in our brackets. And then we only have to write all the things that neon doesn't take care of for us. So remember, the standard electron configuration for magnesium, you can write it right here, was 1s2, 2s2, 2p6, 3s2. Well, the standard electron configuration for neon is 1s2, 2s2, 2p6. by writing down neon, we have cut all of this out. We don't have to write it again. All we have to write is neon and then 3s2, and that's it. Once again, we can still see our valence electrons. Since we're in the second column, we said there should be 2 valence electrons, and we can see right here that there are 2 in our highest energy level, in this third energy level. So as you start moving down the table into more and more electrons, noble gas configuration becomes more and more helpful. Let's see it for arsenic. Arsenic has 33 electrons. Finding it on your table, you can see it right here in the 4p orbitals. So we'll go up 1 row, go all the way to the right. We are going to use argon as our noble gas. So we'll start by writing argon, AR, put it in brackets to show we are using it. And then we only have to write the things that are not taken care of by argon. So the whole third row is taken care of by writing argon. We'll start again on the 4th row, and we just have to write 4s2, 3d10, 4p3. And that's our noble gas configuration for arsenic. Once again, we've got our 2 electrons here and our 3 electrons here in that 4th energy level for a total of 5 valence electrons. All right, last one of our old examples, let's look at cadmium. Cadmium is in the 4d orbitals of your table. Remember, it's the 10th element going into those 4d orbitals. So I will go up 1 row and go all the way to the right, and I will find krypton. So that is the noble gas I'm going to use. I'll write down the symbol Kr for krypton. Oh, remember there are 48 electrons here. And then I just have to write down all the things not taken care of by krypton. So I'll start on the next row after krypton, 5s2, and then 4d10. And that's my noble gas configuration for cadmium. Once again, I can see that these 2 electrons right here in the 5th energy level, those are my 2 valence electrons. All right, our last example here is just sort of to prevent you from making what could be an easy mistake to make. Our next example is argon, right? But argon is a noble gas. Argon has 18 total electrons. The noble gas configuration for argon is not this. Please don't do this. Your noble gas configuration is always in terms of a different noble gas. So for argon, we're going to follow the exact same rules. We're going to go find argon on our table and then go up a row. And the noble gas above argon is neon. So that is the noble gas we will use. We'll write Ne, put it in brackets, and then follow along from there. Ne, neon, finishes row 2. So we'll go look at row 3. 3s2, 3p6 will take us to argon. So 3s2, 3p6. And then to figure out our number of valence electrons, our highest energy level here is the 3rd energy level. So we have 2 electrons here, 3 electrons here, for a total of 8 valence electrons. And these 8 valence electrons, this is going to be sort of a magic number. So keep this in mind, that your noble gas has 8 valence electrons. Everything in that column has 8 valence electrons, and that is a very important property of noble gases. All right, let's look at just a couple more examples here. Going the other way, given a noble gas configuration, figuring out which element you are looking at. Letter A here has us starting with neon. You should go to your periodic table and find neon. And then from neon, go down to the 3rd row. Look at your 3s12 and then 3p123. That is going to give you phosphorus, right? If you look on the 3rd row of your periodic table, find the p block and count across 3 elements, you get phosphorus. The other way to tell is to say, well, neon has 10 electrons plus 2 plus 3, that's 15 electrons. And that is the number of electrons in phosphorus. So that's your other way of knowing. Looking at letter B, find krypton. Go down to the next row and count 5s2 all the way through your 4d orbitals, 4d10, and then look 1, 2, 3 elements into your 5p orbitals. Going across, that will give you antimony. Once again, the other way to check is to find the number of electrons in krypton. Krypton has 36 electrons, plus 2, plus 10, plus 3 gives you 51 electrons, which is the number of electrons in antimony. Our last one, xenon, 6s2, 4f14, 5d6. The last orbitals we're looking at are 5d6 orbitals. Go to your periodic table, find your 5d orbitals. Those are in the 6th row, and count across 1, 2, 3, 4, 5. Or you can also take your electrons in xenon. There are 54 electrons in xenon, plus 2, plus 14, plus 6. Adding those all together gets you 76, which is the atomic number of osmium. You're not going to have to be able to count through your F orbitals. Just wanted to do an example. Things start getting a little fishy when you're counting through your F and your D orbitals, so at that point, your safest bet is just add up all of your electrons and find the correct atomic number. 76 electrons means osmium. Okay, so for the last time, go ahead and turn to pages 18 and 19, fill in those last boxes, the noble gas configurations. Be sure to check your answers against the key on my website. And then pat yourself on the back because this was a marathon video. You learned 3 different notations for writing your electron configurations. The next video is going to talk about a different way to identify electrons. So it'll still be saying, here's this electron, I found that it's in this orbital, but it'll be talking about it in a very different way. So take a well-deserved break after you do your practice. Check out your quest. You can do a fair number of them now. And then when you're ready, go watch the next video. So good luck and happy studying.